exercise 2.3. We now move on, since we already have the spin connection coefficients. We have them. Therefore, we can compute the curvature form, omega, which is given by Cartan's second equation, and we need to prove that at first order it reads like that. So let's do that. We use, as we said, the Cartan structure equation, which is this one. But we need to keep it at first order. So what we notice that we have this exterior product of omega with omega, but omega contains derivative of phi. You see, every time it has a derivative of phi, intact. Therefore, the product of omega with omega is of second order, and therefore we drop it. Boom, this goes away, and we are left only with this one. Therefore, omega is equal to that. So what we are left with is to express explicitly the exterior derivative of omega. We now go for the 0 e component. The 0 is equal to 0 because we have this expression. So we go for the 0 e component, which might be not 0. So let's check. And the omega 0 e is this one. Okay. So we just compute the exterior derivative of that. So which is this one. Then, as we did already for the two-sphere, we express this dx in terms of the dual basis by just simply, see, we need the dxj, so that the space component, that is this one. You see, dxe, and we get our theta e. So we plug this expression into here, obtaining that. Okay? Then we move forward, and we keep on the first order terms, because again, look, we have a phi and a phi here. Therefore, the e phi times 1 is first order, the e phi times phi is second order, because we have the derivative of phi times phi. And what we keep is only this term, leaving us with that. Then again, just for a final touch, we order the bases in terms of their index, and therefore we flip these two guys here, obtaining that. Again, remember when you have the exterior product and you flip the two ingredients, so the exterior product, a -1 pops up. Okay, done. Done for omega 0 e. Now we can continue with the ej, and we do exactly the same thing. There is nothing different. So we need to compute the exterior derivative, this time of small omega ej, and small omega ej, so the spin connection components ej is equal to that. So we just compute the exterior derivative of that expression. Doing that, we have the derivative of a sum is the sum of the derivatives, so we just split the derivatives in this way. We use the explicit expression for the exterior derivative for each of those parts, so that we have this one and this one. And then again, we substitute the x, we express it in terms of the dual basis, obtaining this term. And again, just again for a final touch, we just flip e and k, and k and j, such that we have the k as the last index. Again, this is just a final touch, because this is a dummy index. Okay, so k is repeated. Flip it, doesn't matter much. And that's it for the evaluation of the curvature form.